2,500 years ago, Aristotle put Earth at the center of everything. He was wrong, but he was not being foolish. He was following the most natural intuition a conscious mind can produce. We are here. Everything moves around us. Therefore, here is the center. Science has spent 2.5 millennia systematically proving that intuition incorrect, moving the center from Earth to Sun to nowhere at all. And then quietly, in the data, something started pulling. Every galaxy in our region of the universe falling in the same direction toward the same invisible destination at 630 kilometers per second. Tonight, we find out what that means. Subscribe if this is your first visit here, get comfortable, and stick around because the universe is about to become considerably weirder than you thought. Part 1. The pull we can't explain. Right now, without your permission, without any sensation, without the slightest tremor in the floor beneath your feet, you are moving. Not in the ordinary sense of spinning on Earth's axis, or orbiting the Sun, or even drifting with the solar system through one arm of the Milky Way. Those motions are real and they are staggering on their own. But there is another motion layered on top of all of them, one that operates at a scale so enormous that the entire local group of galaxies, the Milky Way, Andromeda, the Triangulum Galaxy, and more than 50 smaller satellite galaxies is being carried along together as a single coherent unit at roughly 630 kilometers per second. 630. To put that in perspective, the fastest crewed spacecraft ever launched left Earth's gravitational grip at about 11 kilometers per second. The New Horizons probe, humanity's most distant active emissary to the solar system, is currently moving at around 14 kilometers per second. You are, right now, riding something that dwarfs both of those numbers by a factor of more than 40. And the direction is not random. It is not chaotic drift. It is a coordinated fall toward a region of space that, for most of the 20th century, astronomers could not even see. That destination has a name. Astronomers call it the Great Attractor. It sits somewhere between 150 and 250 million light-years away, roughly in the direction of the constellations Centaurus and Norma, positioned just behind the plane of our own galaxy, where the Milky Way's dust and star fill nearly everything from view. The mass concentration there is estimated at around 5 times 10 to the power of 16 solar masses. That number is so large it requires a moment to properly dismantle. The Sun itself weighs roughly 2 times 10 to the power of 30 kilograms. The Great Attractor, by some estimates, contains the gravitational equivalent of 50 quadrillion suns, and for decades we could not observe it directly. We only knew it was there because of what it was doing to everything around it. What it is doing is this. It is pulling, not just our galaxy, not just our local cluster, the entire Virgo supercluster. Hundreds of thousands of galaxies in a region stretching across hundreds of millions of light-years is tilting toward this same point. Galaxies that have no physical connection to each other, separated by distances that light would take millions of years to cross, are all accelerating in the same direction. This is coherent motion. This is structure behaving like it has a target. And here is where the problem begins. Because the physics of the universe, at its most fundamental and most carefully verified level, says the universe has no center, not a hidden center, not a center we haven't found yet, not a center so far away it might as well not exist. The cosmological principle, one of the foundational assumptions of modern cosmology, states that the universe is homogeneous and isotropic on large enough scales. Homogeneous means matter is distributed roughly the same way everywhere. Isotropic means it looks roughly the same in every direction. If both of those things are true, and an enormous body of observational evidence suggests they are, then no location in the universe is special. No point is a privileged origin. No coordinate in the cosmos can claim the title of center, because center only has meaning when you can define an edge, and the universe, as far as current understanding reaches, has neither. So we have a contradiction sitting right at the front door of this conversation. On one side, a universe whose physics actively prohibits a center. On the other, motion so coherent and directional that something must be causing it, something that behaves, from our vantage point, exactly like a center would. That tension is not going to be resolved in a single clean sentence. It is going to take time to properly appreciate, because appreciating it requires understanding both sides in detail, both why the universe genuinely lacks a center in the global sense, and why local structure still produces something that looks and behaves like one. Let's start with what that motion actually means. When astronomers say the local group is moving at 630 kilometers per second, they are not measuring that speed relative to some nearby galaxy or landmark. They are measuring it relative to the cosmic microwave background. The CMB, and we will spend considerable time on this later, is the relic radiation from the early universe, a faint glow of microwaves that fills all of space uniformly, a kind of thermal imprint of the universe when it was roughly 380,000 years old. Because it fills all of space in every direction, it provides something that no other reference point can, a rest frame for the universe itself. Not an absolute frame in the sense that Einstein's relativity prohibits, but a practical rest frame, a background against which motion can be measured in a physically meaningful way. And, relative to that background, everything in the local group, you, this planet, this solar system, this galaxy, all of its satellite galaxies, Andromeda, bearing down on us from 2.5 million light-years away, is moving together at 630 kilometers per second toward the Great Attractor. That motion is what physicists call a peculiar velocity. In cosmology, peculiar velocity refers to the movement of an object over and above the expansion of space itself. When the universe expands, galaxies are carried apart simply because the space between them is stretching. That motion comes for free. The peculiar velocity is different. It is gravitationally induced. It is the speed you acquire because nearby mass is pulling you toward it. And when that peculiar velocity is 630 kilometers per second, the gravitational source responsible for it is not small. It is not local, it is something architectural in scale. Here is a concept worth sitting with for a moment. The idea of a gravitational basin. Imagine water on a gently sloping surface. The water does not know where it is going. It has no intention, no target awareness. It simply flows downhill, always toward the lowest local point it can reach. A gravitational basin works the same way, but the slope is made of space-time rather than physical terrain, and the fluid is galaxies rather than water. What we appear to be inside right now is an enormous gravitational basin, a region of space-time that slopes very gently over hundreds of millions of light-years in the direction of the Great Attractor and the larger structures associated with it. We are not being pulled by a point. We are flowing down an incline the way every galaxy in our local patch of the cosmic web is flowing down an incline, all tilted in roughly the same direction. And the question that has to follow from that picture is the one that will take this entire conversation to properly address. If the universe has no center, if the cosmological principle holds, if the Big Bang did not happen at a point, if expansion proceeds equally in every direction from every observer's perspective, then why is motion aligned across such vast scales? Why does anything point anywhere? What gave the universe a preferred direction, locally or otherwise? There are hints at the answer scattered across different scales. The Great Attractor is real, but it is not the end of the hierarchy. Beyond it sits the Shapley supercluster, several times more massive, pulling from even greater distances. The cosmic web, the filament and node structure that organizes matter across the observable universe, creates a kind of topography in which every region is tilted relative to every other region, and flow is a natural consequence. But there are also anomalies that do not fit cleanly into this picture. A cold spot in the CMB that has no satisfying explanation, a discrepancy in the direction of distant radio sources that should not exist if the universe is truly isotropic. Claimed flows of galaxies on scales so large that the standard model of cosmology struggles to produce them. Each of these anomalies is small on its own. Together, they carry the faint suggestion that the question we are about to dissolve may not be as dissolved as cosmologists would like. That is the terrain we are walking. The problem isn't that we haven't found the center. The problem is that the universe may not be built to have one, and yet something keeps acting like it does. Part 2. The long history of a moving center. For most of recorded human thought, the center of the universe was not a mystery. It was obvious. You could stand outside on a clear night, watch the stars wheel overhead, feel the solid ground beneath your feet, and arrive at a conclusion that seemed not just reasonable but self-evident. Everything moves around us. The earth does not move, the sky does. Therefore, the earth is the center. Aristotle, writing in the 4th century BCE, formalized this intuition into a complete cosmological framework. His universe was made of concentric spheres, with Earth at the middle and the stars fixed to the outermost shell. Objects fell downward toward Earth, because Earth was the natural center of the cosmos. Downward motion was not a gravitational effect, it was a kind of cosmic homecoming. Things moved toward the center, because that is where they belonged. Claudius Ptolemy, writing roughly 500 years later in the 2nd century CE, took that picture and made it mathematically precise. His Almagest described a geocentric system with enough sophistication to predict planetary positions, eclipses, and celestial events with reasonable accuracy. The planets moved in small circles called epicycles, which themselves moved along larger circles called deferents, all of it centered on or near the Earth. It was wrong about almost everything architecturally, but it worked well enough as a predictive tool that it dominated Western astronomy for over 1,000 years. The center was Earth. The universe was a machine built around human habitation. Then Nicolaus Copernicus, in 1543, published his heliocentric model and moved the center. Not far, cosmically speaking, from Earth to the Sun, a shift of about 150 million kilometers, essentially nothing on astronomical scales. But conceptually, it was a rupture. The Earth was no longer special. It was just another planet, circling the same star the others circled. The center had taken its first step toward vanishing. Galileo Galilei, a few decades later, pointed his telescope at Jupiter and found 4 moons orbiting it, not orbiting Earth. Not orbiting the Sunday, orbiting Jupiter. Here were objects that definitively did not circle the cosmic center, whatever that center was. The universe, it turned out, contained multiple gravitational allegiances, multiple local orbits, centers within centers that had nothing to do with Earth or even the Sunday. Isaac Newton completed a crucial step in this retreat. His law of universal gravitation, published in 1687, explained why planets orbit, why tides rise, why apples fall, and it did so without requiring any fixed cosmic center. Gravity was a relationship between masses, not an attraction toward a privileged location. In a Newtonian universe, every massive object attracted every other massive object. The universe had no need for a center to organize its dynamics. The center was not moved again. It was made unnecessary. But psychological persistence is a remarkable thing. Even after Newton, even after Copernicus and Galileo, even as science dismantled every specific candidate for the center, the intuition that there must be one somewhere survived. It migrated. When astronomers in the 18th and 19th centuries mapped the Milky Way, early models placed the solar system near the center of the galaxy. That turned out to be wrong as well. We are about 26,000 light-years from the galactic center, in one of the outer spiral arms, a thoroughly unremarkable address in a galaxy of about 300 billion stars. Then, when it became clear in the 1920s that the Milky Way was just one of billions of galaxies, the instinct reached for a center of the universe itself. Surely, all of these galaxies had to be centered somewhere. The pattern here is visible and worth stating plainly. For 2,000 years, science has not been finding the center. It has been removing false ones. Every time a new candidate was proposed, observation eventually showed it to be an artifact of limited perspective, rather than a genuine cosmic fact. The center has been retreating continuously, and the retreat of that center is not a story of science failing to find something. It is a story of science systematically discovering that the something was never there to find. And that brings us directly back to the central tension of this whole conversation, because modern cosmology does not simply move the center one more time. It removes it entirely. And it does so not by failing to find it, but by demonstrating mathematically and observationally that a centerless universe is not only possible but required by what we actually see, which makes the observed directional motion of 630 kilometers per second all the more puzzling. Because if there is no center, what exactly are we falling toward? Part 3. The equation that broke the universe. In 1929, Edwin Hubble published a result that did not merely extend cosmology, it restructured it completely. Hubble had been measuring the distances to galaxies using a type of variable star called a Cepheid, whose pulsation period is directly related to its intrinsic brightness, allowing it to function as a standard candle, a known brightness against which apparent brightness can be compared to calculate distance. He had also been using redshift measurements, compiled largely by his colleague Vesto Slipher, which revealed that the light from distant galaxies was systematically shifted toward the red end of the spectrum, indicating those galaxies were moving away from us. What Hubble found when he plotted the two datasets together was a relationship so clean it was almost suspicious. The farther away a galaxy was, the faster it was receding. Velocity equaled a constant multiplied by distance. In modern notation, v equals h0 times d. That relationship is called Hubble's law, and it describes a universe that is expanding, not expanding in the sense that galaxies are flying outward through pre-existing empty space from some central explosion. That is the version most people picture, and it is the version that is wrong. The correct picture is stranger and more interesting. Space itself is expanding. The metric of space-time is stretching. Galaxies are not moving through space away from a center. They are being carried apart because the space between them is getting larger. The balloon analogy captures part of this. Imagine dots painted on the surface of an inflating balloon. As the balloon expands, every dot moves away from every other dot. No single dot is the center of the expansion. No dot is special. From the perspective of any dot, all other dots appear to be receding, and the farther away they are, the faster they appear to recede. The surface of the balloon has no center on its surface. The expansion does not originate from any point on the balloon, it originates from within the balloon, in a dimension the surface dwellers cannot access. But here is where the analogy becomes philosophically loaded. The center of the balloon, the point inside the rubber that the surface curves around, does exist, just not on the surface. If the universe is like the surface of the balloon, then any center it might have exists in a spatial dimension we cannot access, outside the observable universe, outside space-time as we experience it. For all practical purposes, for every purpose that involves observable physics, there is no center. Every observer, on every galaxy, in every corner of the universe, measures the same Hubble expansion. Every observer sees all other galaxies receding. Every observer appears, from their own perspective, to be at the center of expansion. And the word appears is doing a great deal of work in that sentence, because the appearance is not illusion exactly. not delusion. It is the mathematical consequence of a space-time that expands uniformly everywhere. Centrality becomes observer-dependent. Every location is the center, which is mathematically equivalent to no location being the center. This is the cosmological principle. The universe, on scales large enough to average over local clustering and structure, is homogeneous, similar in density and composition everywhere, and isotropic, similar in every direction of observation. The cosmological principle is not a philosophical preference. It is an empirical observation supported by decades of galaxy surveys. When you map galaxies across the sky in sufficient numbers and average over large enough volumes, the distribution becomes smooth. The Planck satellite's measurements of the CMB constrain the curvature parameter of the universe to within a tiny fraction of flatness, with the spatial curvature parameter omega k sitting at approximately 0 to within measurement uncertainty. A flat, homogeneous, isotropic, expanding universe does not have a center. The geometry forbids it the same way a perfectly flat, infinite plane forbids an edge. There is a scale threshold where this smoothness kicks in. Below roughly 100 to 250 megaparsecs, where 1 megaparsec equals about 3.26 million light-years, the universe is lumpy. There are galaxy clusters, superclusters, filaments, voids, walls of galaxies that stretch across hundreds of millions of light-years. These structures are real, and they are enormous. But above that scale, averaging over regions larger than several hundred megaparsecs, the universe becomes statistically uniform. Structure persists locally. Globally, the cosmological principle holds, and the principle's most important implication is the absence of any privileged position. But there is a crack in this picture that is worth knowing about before we go further. The Hubble tension. The rate of cosmic expansion, the Hubble constant, h0, can be measured in two fundamentally different ways. One method looks at the early universe, using the CMB and the pattern of acoustic oscillations frozen into it, and extrapolates forward. The Planck satellite collaboration, using this method, arrives at a Hubble constant of roughly 67.4 kilometers per second per megaparsec. The other method measures the expansion rate directly in the local universe, using Cepheid variables and type Ia supernovae as distance ladders. The SH0ES collaboration, using this method, arrives at roughly 73.2 kilometers per second per megaparsec. Those two numbers do not agree. The discrepancy is around 4 to 5 sigma, which in physics is the threshold typically used to claim a discovery. Both measurements are careful. Both teams have checked their work extensively, and the gap between them has not gone away. This tension might be a systematic error that future data will resolve. It might be evidence that the expansion rate has changed in ways the standard model does not account for. It might be pointing at genuinely new physics. No one knows yet, but it is a reminder that even the foundational quantity of cosmic expansion is not pinned down with perfect certainty, and that the neat, centerless, homogeneous picture of the universe rests on a framework that has at least one visible crack running through it. The universe expands like it has no center, because it does, but the rate of that expansion is not as settled as cosmology textbooks sometimes suggest, and that unsettledness is going to matter later. What expansion tells us, though, is this. If every observer sees themselves at the center of expansion, and if every observer is equally correct in that observation, then center has ceased to be a meaningful physical concept in the global sense. The question is not where the center is. The question is whether the concept applies at all. And to fully grasp why it does not, we need to go back to where the expansion began, not backward through space to a specific location, but backward through time to a specific moment. Because the origin of expansion is not a place, it is a condition. And understanding that condition is going to fundamentally change how the question at the center of all of this makes sense. Part 4. The Big Bang didn't happen somewhere. The single most persistent misconception in popular cosmology is a simple one, that the Big Bang was an explosion, that it happened at a specific point in space, and that if you could trace everything backward far enough, you would find that point, the origin, the ground zero, the center. This picture is intuitive because every explosion we have ever witnessed begins at a place. A firecracker, a supernova, a bomb, all of them start at a location and expand outward from that location. So the natural extension is to imagine the universe doing the same thing, only bigger, only at the very beginning, a primordial point, a cosmic pinprick from which all of existence erupted outward. The Big Bang must have happened somewhere. It did not. Or more precisely, it happened everywhere simultaneously, because everywhere was the same place. To understand this, you need to let go of the intuition that space is a container that was empty before the Big Bang and then got filled. Space is not a container that the universe sits inside. Space is a property of the universe itself, one of its dimensions, something that came into existence with the universe and has been expanding ever since. Before the Big Bang, to the extent that before is even a meaningful concept, when time itself did not yet exist, there was no spatial arena waiting for something to happen inside it. The space-time geometry of the universe did not pre-exist the universe. It emerged with it. The Big Bang describes a state. Specifically, it describes a state in which all of space was in an extraordinarily hot, dense condition, where the temperature and energy density were so extreme that matter as we understand it could not exist in its current form. Not a state at a single point in space, a state of all of space. When cosmologists say the universe was once the size of a grapefruit or the size of a proton, what they mean is that the entire observable universe, all of the matter and energy that currently fills a sphere, roughly 93 billion light-years in diameter, was compressed into that volume. Not that the universe existed inside a grapefruit-sized bubble in the middle of a larger, empty space. The entire universe was that grapefruit. There was no outside. This is where space-time diagrams become genuinely useful and also genuinely dangerous. A standard diagram of cosmic history shows time running vertically and space running horizontally, with the Big Bang at the bottom as a narrow point from which everything flares upward and outward. This looks, irresistibly, like an explosion at a point. But the narrowness at the bottom of that diagram represents not a spatial point, but a temporal boundary. All of space was compressed. The width of the diagram at any given time represents the scale of the universe, not the boundary of an expanding shell. The Big Bang sits at the bottom of that diagram the way midnight January 1st sits at the start of a timeline as a temporal boundary, not a spatial location. The cosmic microwave background is the most direct observational evidence for this. The CMB is the light that was released when the universe cooled enough, about 380,000 years after the Big Bang, for electrons and protons to combine into neutral hydrogen. Before that moment, the universe was a plasma so dense and hot that photons could not travel freely. They were constantly absorbed and re-emitted, trapped in a fog of charged particles. When neutral atoms formed, that fog cleared, and the photons that had been trapped were suddenly free to travel in straight lines. They have been traveling ever since. They are what we detect as the CMB. Here is the key point. When we point our instruments at the CMB, we are looking back through time to that moment of recombination, and we detect the CMB not in one direction, not from the location of the Big Bang over there, but from every direction equally. North, south, east, west, up, down, every angle we point at the sky shows us the same faint glow. That is because we are surrounded by that ancient light. The CMB reaches us from a spherical shell called the surface of last scattering, and we sit at the center of that shell not because we are at the center of the universe, But because the surface of last scattering is defined as the distance at which light emitted at recombination is only now arriving at us, every observer in every galaxy sits at the center of their own surface of last scattering. The CMB does not come from a single direction because the Big Bang did not happen in a single direction. It happened everywhere. What you are seeing when you look at the CMB in any given direction is not the place where the Big Bang happened. You are seeing what that direction in space looked like 380,000 years after the CMB. Big Bang? When the universe there released its first free photons, the Big Bang is not a location in space. It is a condition in time, and it happened right here, exactly where you are sitting, at every other point in the universe simultaneously. This matters enormously for the question we are examining, because it means the directional motion we started with the 630 kilometers per second toward the Great Attractor cannot be a remnant of the Big Bang's location. There is no Big Bang location to be a remnant of. The coherent motion we observe is not something inherited from an explosion that happened somewhere else. It is structure built after the Big Bang through the gravitational amplification of tiny quantum fluctuations that has created local slopes in space-time that everything flows toward. And yet, that structure, as we are about to see, is organized enough, directional enough, persistent enough over enormous scales that the question of what produced it and whether the universe is truly centerless in the deepest sense is not entirely closed. What if some of those tiny quantum fluctuations that seeded all this structure were not random? What if the initial conditions of our universe, laid down at or before the Big Bang, were not perfectly isotropic? What if the centerless universe is only centerless within the volume we can observe, and something beyond the horizon is pulling on us from outside? These are not idle speculations. They are the questions that three specific anomalies in the data are quietly asking. But before we can hear those anomalies clearly, we need to understand what a truly centerless universe looks like from the inside, and that requires spending some time with a faint glow that fills all of space and knows exactly how fast you are moving. Part 5. The Universe's Only Reference Frame. In 1964, Arno Penzias and Robert Wilson, working at Bell Laboratories in Holmdel, New Jersey, were trying to eliminate an annoying and persistent noise from a large, horn-shaped radio antenna that had been built to communicate with early telecommunications satellites. The noise came from every direction equally, regardless of where they pointed the antenna. They tried everything to get rid of it, including, famously, cleaning out the pigeon droppings that had accumulated inside the horn. The noise persisted. It turned out not to be an engineering problem. It was, instead, the most important cosmological discovery of the 20th century. They had accidentally detected the cosmic microwave background, the thermal afterglow of the early universe, arriving from all directions at a temperature of roughly 2.725 Kelvin, that is, 2.725 degrees above absolute zero. They won the Nobel Prize in Physics in 1978. The temperature of the CMB, 2.725 Kelvin, is almost perfectly uniform across the entire sky. Almost. If you look with enough precision, you find variations of about 1 part in 100,000 tiny fluctuations in temperature that turn out to be the seeds of all cosmic structure, the quantum whispers that grew, over billions of years, into galaxies and clusters and the cosmic web. These fluctuations carry an enormous amount of information about the early universe, and entire space missions, the COBE satellite in 1989, WMAP in 2001, and Planck from 2009 to 2013, have been devoted to measuring them in exquisite detail. But before you get to those tiny fluctuations, there is a larger variation in the CMB that has to be accounted for: the dipole. The dipole is a pattern in which one side of the sky appears very slightly warmer than the other, and the opposite side appears very slightly cooler. The temperature difference is small, about 3.36 millikelvin, which is 3.36 thousandths of a Kelvin, but it is unmistakable. One half of the sky is fractionally hotter, one half is fractionally cooler, and the variation changes smoothly as you scan across the sky from one direction to the other, exactly as you would expect from the Doppler effect applied to a moving observer. This is a Doppler shift. When we move toward a source of radiation, the waves are compressed and we perceive them as slightly hotter, slightly higher energy. When we move away, the waves are stretched and we perceive them as slightly cooler. The CMB dipole tells us precisely how fast and in what direction the entire solar system is moving relative to the rest frame of the CMB. The answer is 369.82 kilometers per second in the direction of the constellation Leo, with a precision that is genuinely remarkable, not approximately, not roughly. 369.82. Now, that number describes the solar system's motion relative to the CMB. The local group, the Milky Way, and all its neighbors is also moving relative to the CMB. When you account for the Milky Way's motion within the local group, and the local group's motion toward Andromeda and through its local environment, the total velocity of the local group relative to the CMB comes out to approximately 630 kilometers per second. That is the number from the beginning of this conversation, and it is pointed, as we discussed, toward the Great Attractor and the larger structure behind it. What the CMB rest frame represents is something subtle and worth dwelling on. It is not an absolute rest frame in the sense that Einstein's special relativity forbids. Relativity says there is no preferred inertial frame, no frame from which the laws of physics look fundamentally different than from any other. The CMB rest frame does not violate this. It is not a frame in which the laws of physics are different. It is simply a frame in which the CMB appears perfectly isotropic, with no dipole, because you are not moving relative to it. Every observer in the universe, anywhere in the cosmos, can in principle detect the CMB and measure their own velocity relative to this rest frame. Every observer gets a different number, depending on how they are moving. But the frame itself is the same for all of them. It is a universal reference for motion, not a universal reference for position. The universe gives us a way to define speed. It does not give us a way to define location. This distinction sounds like it might be a small technicality, but it is actually the precise boundary between what exists and what does not. A velocity without a position anchor means there is motion but no destination, direction but no center. The CMB tells the local group it is moving at 630 kilometers per second. It does not tell us where we are relative to the universe's origin. It cannot, because the origin was everywhere, and we are as close to it as anything else in existence. What we do get, what the CMB uniquely provides, is a preferred motion without a preferred place. The universe refuses to give us a location, but it gives us a direction, and in that direction, something is waiting. Something that began as an anomaly in galaxy velocity surveys and turned out to be one of the most gravitationally influential structures in the local cosmos. Part 6. The invisible mass we're falling toward. The Great Attractor was not discovered by seeing it. It was discovered by noticing that everything around us is moving. In the 1980s, a group of 7 astronomers, Alan Dressler, Sandra Faber, David Burstein, Roger Davies, Donald Lynden Bell, Roberto Turlevich, and Gary Wegner, collectively known as the 7 Samurai, undertook a systematic survey of elliptical galaxies across a large portion of the sky. Their goal was to use a relationship called the Faber-Jackson relation, which connects the luminosity of an elliptical galaxy to the internal velocities of its stars as a distance indicator. By comparing how far a galaxy appeared to be from its redshift with how far it actually was from its Faber-Jackson distance, they could infer whether it was moving faster or slower than pure cosmic expansion would predict. These deviations from pure Hubble flow are the peculiar velocities, the gravitationally induced motions, on top of expansion. What the Seven Samurai found, published in 1988, was that galaxies across an enormous region of sky, stretching across hundreds of millions of light-years, were all moving in the same direction. Not randomly, not in the small, localized way you might expect from ordinary galaxy clustering, coherently, directionally, as if being drawn toward something. Something located roughly in the direction of Centaurus and Norma, at a distance of perhaps 150 million light-years, behind the plane of the Milky Way, where optical observation is nearly impossible. They called the source of this gravitational pull the Great Attractor, and for years they could not see what it was. The problem is the zone of avoidance. The Milky Way is not a translucent disk. It is a disk packed with stars, gas, and dust, and when you try to look through it in optical wavelengths, you are blocked. About 20% of the sky is heavily obscured by our own galaxy. The Great Attractor sits almost exactly in this obscured region. Astronomers have had to piece together its nature using X-ray observations, radio wavelengths, and infrared surveys that can penetrate the galactic plane to varying degrees. What they have found, gradually, is that the gravitational concentration the Seven Samurai detected corresponds primarily to a structure called the Norma cluster, or Abell 3627, a rich galaxy cluster near the center of the Norma supercluster. But the Norma cluster alone is not enough to account for all of the observed motion. The Great Attractor is not a single object. It is a region, a concentration zone in the cosmic web, where multiple clusters and filaments have accumulated into a gravitational basin of extraordinary scale. The mass estimates for the Great Attractor are genuinely staggering. Roughly 5 times 10 to the power of 16 solar masses is a commonly cited figure, though estimates vary depending on exactly how much of the region is included and how the measurement is made. To help put that in context, the Milky Way, with its dark matter halo, contains something on the order of 1 to 2 trillion solar masses. The entire Virgo cluster, the nearest major galaxy cluster, contains something like 1 quadrillion solar masses. The Great Attractor region contains tens to hundreds of times more than the Virgo cluster. It is, by any reasonable measure, a gravitational colossus. And yet, here is a detail that tends to produce a particular kind of quiet, existential recalibration. We are already past it. The cosmic expansion of the universe and the geometry of our peculiar motion mean that, in a few billion years, the expansion of space will begin to overwhelm the gravitational pull of the Great Attractor at the distances involved. Our motion toward it will slow and eventually cease in terms of closing the distance, not because the mass goes away, but because space is expanding faster than we are falling. More to the point, the Great Attractor is not the end of the hierarchy. It is a basin within a larger basin. The Great Attractor itself is being pulled towards something larger, more distant, and even harder to observe. We are falling toward the Great Attractor the way a river flows toward a lake, and the lake is itself draining toward the ocean. We are falling, but not to the bottom. The bottom, whatever it is further away than the Great Attractor, and it has a name. Part 7. Behind the Attractor, the Larger Pull. Harlow Shapley was one of the most important astronomers of the 20th century, though perhaps not primarily for the discovery that bears his name in this context. Shapley was brilliant, prolific, and spectacularly wrong about one of the biggest questions of his era, and the story of how he was wrong is worth telling before we get to the thing he was accidentally right about, because it illustrates something important about how science works and how the universe has a way of making even its most confident interpreters look small. In the 1920s, Shapley was engaged in one of the most consequential scientific debates in the history of astronomy. The question was deceptively simple. What are the fuzzy patches of light scattered across the sky that astronomers were calling spiral nebulae? Were they clouds of gas and dust within the Milky Way, relatively nearby objects embedded in our own galaxy? Or were they independent island universes, entire galaxies in their own right, separated from us by distances so enormous that the human mind had no real framework for comprehending them? Shapley argued for the first option. He believed the Milky Way was enormous, perhaps 300,000 light-years across, and that these nebulae were internal features of it. His opponent in the Great Debate of 1920, an astronomer named Heber Curtis, argued the opposite. The spiral nebulae were external galaxies. The Milky Way was much smaller than Shapley claimed, and the universe was vastly larger than anyone had seriously reckoned with. Shapley lost. Edwin Hubble's distance measurements to the Andromeda Nebula in 1923 settled the matter decisively. Andromeda was not a cloud of gas inside the Milky Way. It was a galaxy roughly the same size as ours, sitting about 900,000 light-years away, a number that has since been revised upward to about 2.5 million light-years as measurement techniques improved. The universe was not the size Shapley imagined. It was incomparably larger. The spiral nebulae were galaxies, billions of them, each containing billions of stars, scattered across a cosmos that dwarfed every previous conception of it. But decades later, Shapley's name became attached to something far larger than even his overstated Milky Way. The Shapley supercluster, identified and characterized through the second half of the 20th century and increasingly well mapped in the 21st, is a structure of such enormous mass and gravitational influence that it is now understood to be the single dominant gravitational force shaping motion across our entire regional universe. The man who underestimated the universe ended up having his name on one of the largest things in it. There is something satisfying about that. The Shapley supercluster sits roughly 650 million light-years away in the direction of the Centaurus Hydra region of the sky, significantly farther than the Great Attractor, which sits at roughly 150 to 250 million light-years. Its mass is estimated at more than 10 to the power of 17 solar masses. To give that number some texture, one solar mass is the mass of our Sun, which itself contains about 99.8% of all the mass in the solar system. 10 to the power of 17 solar masses is 100 million billion times that. It is a number that resists intuition entirely. You cannot picture it. You can only acknowledge it and move on. Some estimates of Shapley's total mass, when the extended infall region around its core is included, place it even higher. It contains dozens of rich galaxy clusters, hundreds of individual galaxy groups, and thousands of catalogued galaxies in its densest regions. It is the most massive known concentration of matter, within approximately 1 billion light-years of the Milky Way, and its gravitational reach extends across the entire local supercluster complex in a way that shapes the motion of everything within that volume. The relationship between the Shapley supercluster and the Great Attractor is one of gravitational hierarchy, an understanding that hierarchy is the key to understanding why our motion has the direction it does. The Great Attractor is real. The mass concentration in the Centaurus Norma region genuinely pulls on the local group, and that pull contributes meaningfully to our peculiar velocity. But the Great Attractor is not the final word. It is itself being pulled. The Great Attractor flows toward Shapley the same way the local group flows toward the Great Attractor, not because anything is physically chasing anything else, but because the gravitational slope of space-time in our region of the cosmos tilts, at every scale, in roughly the same direction. Studies of galaxy peculiar velocities published across the 2000s and into the 2010s have found, consistently, that when you correct for the Great Attractor's influence and subtract its contribution to the observed peculiar velocity field, a residual motion remains, and that residual points deeper into the same region of sky toward Shapley. Correct for Shapley, and you find the residual diminishes substantially. The cascade is real. We are not falling toward the Great Attractor as a final destination. We are falling through it, towards something behind it, the way a river does not stop at the first lake it encounters if that lake has its own outlet to the sea. The image that best captures this is water flowing downhill. Each step of the hierarchy is a lower elevation than the one before it. The local group is higher, gravitationally speaking, than the Virgo cluster region. The Virgo cluster region is higher than the Great Attractor. The Great Attractor is higher than Shapley. The whole structure is a slope, not a cliff, a gentle, vast incline built from the accumulated gravitational influence of billions of solar masses tilted toward the most massive concentration in our cosmic neighborhood. And this slope did not appear overnight. It took billions of years to build, and its construction began with something so small it barely registers as physical. The origin of all this structure, Shapley, the Great Attractor, the cosmic web itself, traces back to quantum fluctuations in the density of the early universe. In the first fractions of a second after the Big Bang, when the universe was a hot, dense plasma of particles and energy, quantum mechanical processes introduced tiny, random variations in how densely matter was packed from one region to another. These variations were extraordinarily small. We are talking about density differences of roughly 1 part in 100,000, a fluctuation so subtle that if you scaled the entire observable universe down to the size of a basketball, the density variation across its surface would be smaller than a single atom. And yet gravity is patient. Gravity does not forget. Over hundreds of millions of years, the fractionally denser regions attracted more matter from their surroundings, becoming denser still. The fractionally emptier regions gave up their matter to the denser neighbors, becoming emptier still. A feedback loop, running on nothing but the geometry of space-time, amplified those initial 1 part in 100,000 whispers into the large-scale structure of the universe we observe today. The denser regions collapsed under their own gravity and fragmented into the first stars, which ignited a few 100 million years after the Big Bang. Those stars organized into the first galaxies. The galaxies were drawn together by gravity into groups and clusters. The clusters were drawn together into superclusters, and the superclusters arranged themselves over billions of years into the structure cosmologists call the cosmic web, a three-dimensional network of filaments, walls, and nodes surrounding enormous empty regions called voids. The filaments are long, thin strands of matter, sometimes hundreds of millions of light-years long, connecting the massive nodes where clusters and superclusters sit. The voids are the spaces between regions of space where matter has been systematically evacuated by the same gravitational processes that built the filaments. The voids are not empty in an absolute sense. They contain some galaxies, but they are far below the cosmic average density, and they cover the majority of the universe's volume. The cosmic web is mostly nothing, threaded by rivers of something, pooling at junctions of extraordinary mass. The Milky Way sits in one of those filaments. The filament connects to the Virgo cluster, one of the most massive nearby galaxy clusters, sitting about 53 million light-years away. The Virgo cluster is a node that connects to larger filaments leading toward the Great Attractor region, which is itself a node connecting to even larger filaments leading toward Shapley. Every concentration of mass in this hierarchy is simultaneously an attractor for the matter around it and a waypoint in a larger flow directed toward the next, more massive concentration up the chain. Every node is a local center. Every local center is a transit point. And the chain keeps going until, at large enough scales, the nodes average out into statistical uniformity and the concept of center stops applying. Here is the philosophical weight embedded in that structure. What we have been calling a center throughout this entire conversation is really just a description of local gravitational topology, where the slopes are, which way the valleys run, how the terrain of space-time is organized at a given scale. The Great Attractor is a center for our region, in the same way that the Virgo cluster is a center for the smaller scale inside it, and Shapley is a center for the larger scale that contains both of them. Zoom out far enough, and all of these centers dissolve into larger patterns that have their own centers, and those dissolve into still larger patterns until eventually you reach the scale at which everything averages out, and the very idea of center becomes meaningless. Center is not a property the universe has. It is a property the observer assigns, and it depends entirely on the scale the observer is working at. Zoom in, and everything has a center. Zoom out enough, and nothing does. The universe is scale-dependent, all the way down and all the way up. But here is the question that has been building quietly underneath everything we have covered, and it deserves to be stated plainly because it runs directly back to the tension we started with. If all of these centers are scale-dependent, if they are just local features of a random web seeded by random quantum fluctuations, why do they align as well as they do? The Great Attractor, the Shapley supercluster, and the broader peculiar velocity field of our region all point in roughly the same part of the sky. Our motion is not scattered randomly across the celestial sphere. It has a direction, a consistent, persistent, large-scale direction. The cosmic web creates structure, yes, but the web was seeded by fluctuations that should be statistically random on large scales, meaning the flows in our region should not look dramatically different from the flows in any other region, and the overall distribution of attractors and repellers should produce motions that average out to near zero when you look across a large enough volume. So why does our particular corner of the universe have such a clear directional bias? Why does the slope run so consistently toward the Centaurus Hydra region? Is it just the luck of where we happen to sit in the cosmic web, a region that, by statistical chance, has an unusually large mass concentration on one side and an unusually large void on the other, producing a motion that looks more directed than average? Or is there something deeper, something that extends beyond the scale at which the cosmological principle is supposed to smooth everything out? Something, perhaps, beyond the boundary of what we can observe at all. That last possibility is not idle speculation. It is a live scientific question. And 3 pieces of evidence, sitting quietly at the edges of the observational data, are keeping it alive in ways that the standard model of cosmology has not fully answered. The direction problem is real. The question of how far it reaches is open, and the answer, if one exists, may be hiding in a place we are physically incapable of looking beyond the horizon of the observable universe, in the darkness past the last photon that has had time to reach us. The deeper you look, the more centers you find, and the less any of them matter globally, until, perhaps, one of them does. Part 8. Our True Address in the Universe. In September 2014, a paper published in the journal Nature changed the way astronomers think about where we live, not in the small sense of updating a catalogue entry or refining a distance measurement, in the large sense, the fundamental sense, the sense in which the answer to the question, "Where are you from?" asked at the largest possible scale, turned out to be a place that had not been recognized as a place until that moment. The authors were Brent Tully, Hélène Courtois, Yehuda Hoffman, and Daniel Pomared, and what they did was take a dataset of peculiar velocities for roughly 8,000 galaxies, a survey called the Cosmic Flows Catalogue, and use it to map the gravitational flow field across an enormous volume of space, not just the positions of galaxies, not just their redshifts, the actual directions in which they were moving, above and beyond the expansion of space under the influence of gravity. And when they traced those flows, they found something that had been hiding in plain sight for decades, a supercluster so large that no one had previously recognized it as a single, coherent structure. They called it Laniakea. The name comes from Hawaiian, and it means immeasurable heaven. It was chosen partly in recognition of the observatories on Mauna Kea in Hawaii that have contributed so much to our understanding of the large-scale universe, and partly because the name is simply accurate. Immeasurable is not hyperbole when applied to Laniakea. It is a reasonable description of something that extends across roughly 520 million light-years and contains approximately 100,000 galaxies. To put 520 million light-years in perspective, the distance from Earth to the nearest star, Proxima Centauri, is about 4.2 light-years. The distance across the Milky Way is about 100,000 light-years. The distance to the Andromeda Galaxy is about 2.5 million light-years. Laniakea spans 520 million. It is not a structure you can hold in your head by scaling up from familiar things. It is a structure that requires you to abandon familiar scaling entirely and simply accept the number. Within Laniakea sits the Milky Way, the Andromeda Galaxy, the Triangulum Galaxy, the entire local group of more than 50 galaxies, the Virgo cluster with its roughly 1,300 member galaxies, the Fornax cluster, the Centaurus cluster, and dozens of smaller groups and clusters. All of these structures, previously understood as separate entities with their own individual dynamics, turn out to be components of a single gravitational basin. They are all, in the language Tully and his colleagues introduced, flowing toward the same drain. But here is what makes Laniakea genuinely unusual as a cosmic structure, and what separates it from older definitions of superclusters. Laniakea is not defined by gravitational binding. In the strict physical sense, most of Laniakea is not a bound structure. The expansion of space, driven by dark energy, is strong enough across Laniakea's 520 million light-year extent that the gravity holding the whole thing together is not sufficient to overcome it. Over cosmic time, the outer regions of Laniakea will be pulled apart by expansion. Galaxies near the boundaries of the supercluster will eventually drift away, carried by the expansion of space faster than gravity can reel them back. In a few billion years, Laniakea, as a coherent gravitational entity, will begin to dissolve. What Tully's team mapped is not a permanently bound object. It is a snapshot of a flow pattern that exists now, in this era of cosmic history, before expansion has had time to fully disrupt it. This is why the watershed concept is the right one to use, and it is worth spending a moment with the analogy because it is genuinely illuminating rather than merely decorative. A watershed, on land, is the region of terrain from which all water drains to the same river system. You can draw a line across a mountain range, the Continental Divide in North America, for example, and every raindrop that falls on the western side of that line eventually finds its way to the Pacific Ocean, while every raindrop on the eastern side eventually finds its way to the Atlantic or the Gulf of Mexico. The line itself is called the divide. Water on the line could go either way. Water on either side has a determined destination, not because anything is pushing it there, but because the shape of the terrain makes one direction downhill and the other direction uphill. Tully and his colleagues applied this concept in 3 dimensions to the velocity field of galaxies. They traced the peculiar velocity vectors, the directions and speeds of gravitational infall for thousands of galaxies across a huge volume of space, and asked, where does each galaxy's flow ultimately converge? In some regions, everything converges toward the Great Attractor basin in Centaurus Norma. In other regions, flows converge toward the Perseus-Pisces supercluster or the Coma supercluster or other large concentrations. The boundaries between these convergent zones, the cosmic equivalents of continental divides, define the edges of each supercluster. Laniakea's boundary is the surface in 3-dimensional space across which the flow direction changes. Inside Laniakea, everything flows inward toward the Great Attractor. Outside it, flows are directed elsewhere. The boundary is not a wall. It is a ridge, a watershed divide in the gravitational terrain of the cosmos. Our full cosmic address, then, stated from smallest to largest scale, reads something like this: Earth, orbiting the Sun, in the Solar System, in the Orion arm of the Milky Way galaxy, in the local group, in the Virgo supercluster, which is the inner, denser portion of Laniakea in the Laniakea supercluster, in the observable universe. Each level of that address has its own gravitational organization, its own local center, its own flow dynamics. The Solar System orbits the galactic center. The Milky Way orbits within the local group's common center of mass. The local group falls toward the Virgo cluster. The Virgo cluster and everything around it flows toward the Great Attractor. And the whole of Laniakea is itself flowing toward the Shapley supercluster, the gravitational colossus sitting 650 million light-years away that we discussed earlier. The address is real. It is specific. We are not homeless in a featureless, undifferentiated cosmos. We have a location, a neighborhood, a region, a supercluster, and a direction of travel. We are embedded in gravitational topology, the way a city is embedded in geography, not randomly placed, but situated within a specific landscape that shapes everything about how things move around it. And yet, and this is the crucial qualification that has to follow any description of Laniakea, none of this constitutes a center of the universe. Laniakea is one of an estimated million superclusters in the observable universe. The Perseus-Pisces supercluster on the other side of Laniakea's watershed boundary is not lesser or greater than Laniakea in any cosmically meaningful sense. It is simply a different basin with its own attractor, its own member galaxies, its own internal flow patterns. The Coma supercluster, sitting about 340 million light-years away, is a comparable structure. The Hercules supercluster, the Sloan Great Wall, a filamentary structure stretching across about 1.4 billion light-years, one of the largest known structures in the observable universe. All of these are roughly equivalent features in a cosmic web that, at the largest scales, is statistically smooth. Zoomed out far enough, Laniakea is just one basin in a landscape of basins. A significant basin from our perspective, because we happen to live in it, but not special in any objective, observer, independent sense. The Mississippi River's watershed is real, and it is enormous, and it organizes the drainage of about 40% of the continental United States. But it does not define the center of North America. It defines the topology of one region, of one continent, on one planet. Laniakea defines the gravitational topology of one supercluster in one region of one observable universe, that may itself be a tiny fraction of a much larger cosmos. Our local center is real. The universe's center is not. What the Laniakea discovery gives us, then, is not a center. It gives us something more interesting and, in a way, more personal, a dynamic definition of home. Our address is not fixed by static spatial coordinates, the way a street address is fixed by where a building was constructed. It is defined by motion. We belong to Laniakea because we flow toward its attractor. Our membership in this supercluster is not a matter of position alone. It is a matter of gravitational allegiance. If the mass distribution of the universe in our neighborhood were different, if the Great Attractor were less massive, or if a comparable concentration existed in a different direction, or if the void on the opposite side were less pronounced, our gravitational watershed boundary would be in a different place, and we might belong to a different supercluster entirely. Home, at the cosmic scale, is defined by where gravity is pointing you, not by where you happen to be sitting right now. There is something quietly profound about that. Every human definition of home involves some combination of place and belonging, a location, plus a set of relationships and allegiances that make that location meaningful. Laniakea encodes both of those things in a single physical concept. We are here, in this specific location in the cosmos. And we belong here, in the sense that the gravitational geometry of this region of the universe draws us toward its center, incorporates our motion into its flow, makes us a contributing part of its coherent dynamics. We are not just located in Laniakea, we are participants in it. And here is the open question that the Laniakea picture leaves hanging, one that connects directly back to everything we have been building. Laniakea flows toward the Great Attractor. The Great Attractor flows toward Shapley. What does Shapley flow toward? Is there a next level in the hierarchy? A structure beyond Shapley that is pulling on it the way Shapley pulls on the Great Attractor? Some studies of very large-scale peculiar velocities suggest there may be. The motion of matter in our region of the universe, when traced far enough and corrected for the known attractors, does not obviously converge to rest. There may be additional mass concentrations at even greater distances, perhaps approaching or exceeding the scale of the observable universe itself, that are contributing to the flow. And if that is the case, if the hierarchy extends all the way to the edge of what we can see, and perhaps beyond it, then the question of what is ultimately pulling on everything in our cosmic neighborhood becomes a question about the structure of the universe on its largest scales. Scales that may exceed our horizon. Scales that may be, in the most literal physical sense, unobservable. Gravity, as we are about to see, does not only pull toward mass, it effectively pushes away from emptiness. And in the cosmic web, emptiness is not passive. It is active, organized, and powerful in ways that took decades to recognize and are still being mapped. The absence of mass, it turns out, can shape the flow of galaxies almost as decisively as the presence of it. And in the direction opposite to the Great Attractor, something is doing exactly that. Part 9. The Anti-Center. In 2017, a team of researchers led by Yehuda Hoffman published a study that gave a name to something cosmologists had suspected for years but never cleanly isolated. They called it the dipole repeller, and the name immediately raised a question that the paper itself was careful to address, because it sounds, on the surface, like it contradicts one of the most basic facts in physics. The universe does not repel things. Gravity is not a force that pushes. Every massive object in the cosmos attracts every other massive object, always, without exception. There is no anti-gravity in the Newtonian sense, no cosmic force that reaches out and shoves galaxies away from a source. So what does it mean to call something a repeller? It means this. In the context of the large-scale flow of galaxies, a region of space that is significantly less dense than the cosmic average produces an effect that is functionally indistinguishable from repulsion, even though no actual repulsive force is operating. To understand why, you need to think about what drives peculiar velocity in the first place. Galaxies do not move at random. They move in response to the gravitational field around them, which is shaped by the distribution of mass in their neighborhood. In a perfectly uniform universe, one where matter was spread absolutely evenly in every direction, there would be no peculiar velocities at all. Every gravitational pull from every direction would cancel every other pull, and nothing would move relative to the cosmic expansion. Peculiar velocities exist because the universe is not uniform. Matter is clumped. Some regions are denser than average. Some regions are emptier than average. And the gravitational gradient between those regions, the slope between the overdense and the underdense, is what drives everything to move. Now imagine you are sitting at the edge of an enormous void. In one direction, there is a rich filament of the cosmic web, dense with galaxy clusters and supercluster nodes, pulling on you gravitationally. In the other direction, there is the void nearly empty, containing far less mass than the cosmic average, pulling on you with a gravitational force far weaker than the filament on the other side. The net result is that you accelerate toward the filament, not because the void is pushing you, but because the void is failing to pull you back. In a universe where the average gravitational environment pulls equally in every direction, a void is a region where the pull from one side is missing, and that missing pull has the same effect on your motion as a push from that direction would. The void does not repel. It simply fails to attract, and in a universe where everything else is attracting, that failure is dynamically equivalent to a repulsive force. This is what the dipole repeller is. It is a large supervoid, a region of space substantially below the cosmic average density, sitting in roughly the direction of the constellations Gemini and Canis Major, on the opposite side of the local group from the Great Attractor. If you drew a line through the Milky Way pointing toward the Great Attractor in the direction of Centaurus and Norma, the dipole repeller would sit at the far end of that line, in the direction you would be looking if you turned around and faced away from where we are falling. It is, in the most literal sense, the other pole of our cosmic motion. One end of our axis of peculiar velocity is defined by the greatest concentration of mass in our regional universe. The other end is defined by one of the greatest absences of mass. The Hoffman team's paper used an updated version of the Cosmic Flows Velocity Catalogue, the same dataset that Tully and colleagues had used to define Laniakea 3 years earlier, and modelled the three-dimensional density and velocity fields across a large volume of space. What they found was that the observed motion of the local group at 630 kilometers per second toward the Great Attractor region could not be fully accounted for by the gravitational pull of known overdensities alone. When you added up all the mass concentrations in the direction of motion, the Virgo cluster, the Great Attractor, the Shapley supercluster, everything on the attractor side of our peculiar velocity axis, the numbers came up short. The predicted velocity from those sources alone was real and significant, but it did not explain the full 630. Something was missing. What was missing was the contribution from the void on the other side. When Hoffman's team included the underdensity in the Gemini-Canis Major direction in their model, when they properly accounted for the absence of gravitational pull from that side, the numbers came together. The full peculiar velocity of the local group turned out to be a combination of two effects operating simultaneously: the pull of the Great Attractor and Shapley from one side, and the effective push of the dipole repeller from the other. Roughly speaking, the attractor side contributes somewhat more than half of the total velocity, and the repeller side contributes the remainder. The exact division depends on how the density field is modelled and which structures are included, but the basic picture is clear. We are being pulled and we are being freed from counterpull at the same time, and both effects are necessary to explain what we actually observe. This push-pull dynamic is not unique to our neighbourhood. It is the standard operating architecture of the cosmic web everywhere you look. Every filament exists because the voids around it have been evacuated. Every cluster is massive because it has drawn matter from a surrounding region that is now depleted. Every attractor is paired, somewhere in the background, with a region that gave up its matter to build it. The cosmic web is not a collection of dense things sitting in empty space. It is a coupled system in which density and underdensity are two sides of the same gravitational process. You cannot have one without the other. The Shapley supercluster is as massive as it is partly because the voids on its far side are as empty as they are. The dipole repeller is as empty as it is partly because the Great Attractor pulled matter away from it over billions of years. They are gravitational partners, linked by the flow of matter that has been running between them since the early universe. What this means for the central question of this conversation, whether the universe has a center, and what it means that we are moving so fast in a specific direction, is something worth pausing on. The existence of the dipole repeller tells us that our peculiar velocity does not require a single, massive source pulling us from one direction. It does not require anything that resembles a cosmic center, a privileged point, an origin toward which everything is converging. What it requires is simply an asymmetry in the distribution of matter. More mass on one side, less on the other. A gradient. A slope. The motion emerges naturally from the topology of the local cosmic web, without any need for a center to organize it. A direction, in other words, does not imply a center. This is a subtle but important point. We are moving in a specific direction. That direction is real and measurable with extraordinary precision. But a direction is defined by two poles, not by an origin. An axis has two ends. A line has orientation without having a privileged point along it. The universe has given us motion with a direction. It has not given us motion toward a center. The attractor end of our axis is where more mass happens to be. The repeller end is where less mass happens to be. Neither end is cosmically special. They are just the two sides of a local density gradient that happens to be unusually large and unusually well aligned. There is also something interesting in the geometry of the dipole repeller that is easy to miss. The name dipole comes from the fact that this structure, combined with the Great Attractor on the opposite side, produces a dipole pattern in the velocity field, a flow that goes predominantly in one direction across the local volume of the universe. The CMB dipole we discussed earlier, the slight temperature asymmetry caused by our motion relative to the CMB rest frame, is the observational signature of exactly this flow. When Penzias and Wilson's successors mapped the CMB with sufficient precision to detect the dipole, what they were measuring was the net result of the attractor-repeller system we have been describing. The Great Attractor pulls, the dipole-repeller releases. The net effect is a motion of 630 kilometers per second in a specific direction, and that motion imprints itself on the CMB as a fractional temperature difference of 3.36 millikelvin between the hot hemisphere and the cold hemisphere. The dipole in the CMB is, in this sense, a summary statistic of the entire gravitational landscape of our local cosmic environment, compressed into a single measurable number. Now, here is where the picture gets complicated in a way that matters. The dipole repeller, as identified by Hoffman's team, is a relatively well-characterized structure within the volume covered by the cosmic flows, survey a few hundred megaparsecs in radius. But the peculiar velocity field does not stop at the edge of that survey. The universe continues beyond it, and the density field beyond the survey volume is not perfectly well characterized. There are hints in the data that the flow pattern on very large scales approaching and potentially exceeding 1 gigaparsec, which is roughly 3.26 billion light-years, may not be fully explained by the known attractor-repeller system within the survey volume. Some analyses suggest residual flows that point in roughly the same direction as our local motion, extending to distances where the standard model of structure formation has difficulty producing flows of the observed amplitude. These are the anomalies that will occupy us shortly. But before we get there, the dipole repeller gives us one more thing worth holding on to. It gives us a cleaner and more complete picture of why the local group moves the way it does, and in doing so, it reinforces the conclusion that direction does not require a center. We are moving because the universe around us is not symmetric. It never was, and it never will be, because the quantum fluctuations that seeded cosmic structure were random, and random processes do not produce perfect symmetry. Our particular corner of the cosmic web happened to grow a massive supercluster complex on one side and a significant void on the other. That asymmetry drives our motion. It does not point back to an origin. It does not define a center. It is simply the shape of things here, in this particular basin of the cosmic web, at this particular moment in the history of the universe. The standard picture, taken as a whole, is coherent and well supported. The universe has no center. Our motion has a direction. The direction emerges from local density asymmetry. The asymmetry is a consequence of the random seeding of structure by inflation. Everything fits, except for three things. Three observations sitting at the edges of the data that have been quietly declining to be explained away for years. Each of them is small on its own. Each has a possible mundane explanation. But each of them has also refused to fully disappear under scrutiny, and together they carry the faint but persistent suggestion that the perfectly symmetric, perfectly centerless universe the Standard Model describes may be missing something. Something that may not be local. Nay, something that may not be explainable by the density field within our observable horizon. Something, perhaps, that lies beyond the last distance we can see in the darkness past the edge of everything, pulling on our corner of the cosmos from a place we may never be able to directly observe. That is where we are going next. Part 10. The Cold Spot, a Scar in the Sky. In the CMB maps produced by the WMAP satellite and later confirmed by Planck, almost everything is consistent with a random distribution of tiny temperature fluctuations generated by quantum processes in the early universe. Almost everything. And that word almost is doing more work than it appears to be doing, because the exception it introduces is not a minor footnote or a rounding error at the edge of measurement precision. It is a feature in the most important map humanity has ever made, a feature that has survived 2 generations of increasingly sensitive instruments, attracted decades of serious scientific attention, and still does not have a fully satisfying explanation. It is called the cold spot, and it sits in a region of sky corresponding to the constellation Eridanus in the southern celestial hemisphere, quietly defying every attempt to make it unremarkable. To appreciate why the cold spot matters, you need to understand what the CMB is and what it is supposed to look like. The cosmic microwave background is the thermal afterglow of the early universe, the light released roughly 380,000 years after the Big Bang, when the cosmos cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before that moment, the universe was a plasma, a hot, dense fog of charged particles through which photons could not travel freely. They were constantly absorbed and re-emitted, trapped, bouncing around like light inside a frosted glass. When neutral atoms formed, the fog cleared. Photons escaped and have been travelling freely ever since, cooling as the universe expanded. And today they arrive at our instruments as microwave radiation with a temperature of approximately 2.725 Kelvin, filling the sky in every direction uniformly. Almost uniformly. The CMB is not perfectly smooth. If it were, the universe would still be smooth today. No galaxies, no stars, no planets, no anything. The slight temperature variations in the CMB fluctuations, at the level of about 1 part in 100,000, are the imprints of the quantum density variations in the early universe that seeded all subsequent structure. They are the baby pictures of everything that exists. And the physics of how those fluctuations should be distributed is extremely well understood. They should follow what is called a Gaussian random field, a statistical distribution where fluctuations of a given size and temperature contrast appear with a predictable frequency. Large fluctuations are rare, small fluctuations are common, and there are no preferred directions or special locations. The CMB should look, statistically speaking, like a random sprinkling of hot and cold patches with a specific size distribution, symmetric across the sky, unremarkable in any particular direction. And for the vast majority of the sky, that is exactly what WMAP and Planck found. The temperature maps are strikingly consistent with theoretical predictions. The acoustic peaks in the CMB power spectrum, the characteristic size scales of the fluctuations, set by sound waves in the early universe, plasma match the predictions of the standard cosmological model with extraordinary precision. The data is, overall, a triumph of modern cosmology. But, in the direction of Eridanus, there is a cold region roughly 5 degrees across about 10 times the diameter of the full moon, as seen from Earth. That is approximately 70 microkelvin cooler than its surroundings. 70 microkelvin is 70 millionths of a Kelvin. That sounds negligible. It is not. In the context of CMB fluctuations, which are themselves only tens of microkelvin in amplitude, a coherent cold region of this size and depth is a statistical outlier at a significance level above 3 sigma. In plain terms, if the universe is what the standard model says it is, a feature like this should appear by chance less than about once in every few hundred realizations of a universe with the same underlying physics. We appear to have drawn the short straw. Or something is producing this feature that the standard model does not account for. The most straightforward explanation, the one that requires the least deviation from standard cosmology, invokes a physical process called the integrated Sachs-Wolf effect. Here is how it works. When a photon travels through the universe, it passes through regions of varying density. When it enters a gravitational well, a dense region, it gains energy, blue shifting slightly. When it exits the other side, it loses that energy, red shifting back. In a universe that is not accelerating, these two effects cancel perfectly, and the photon exits with the same energy it had going in. But we do not live in a non-accelerating universe. We live in a universe dominated by dark energy, which is causing the expansion of space to accelerate. In such a universe, the gravitational wells themselves are changing while the photon is inside them. A photon entering a large void and underdense region loses energy on the way in and does not fully recover it on the way out, because the void has expanded slightly during the photon's transit, making the far side of the gravitational landscape shallower than the near side. The net result is that photons passing through large voids arrive at us slightly cooler than they would otherwise be. This is the integrated Sachs-Wolf effect, and it is a real, measured phenomenon that has been confirmed in multiple studies. For the integrated Sachs-Wolf effect to explain the cold spot, there would need to be an unusually large and deep supervoid in the direction of Eridanus, at a distance of roughly 2 to 3 billion light-years. And here is where things get interesting, because there is evidence for such a void. Several galaxy surveys over the past 2 decades have detected an underdensity in that direction, a region where the number of galaxies is substantially below the cosmic average across a volume of space that is genuinely enormous. A study published in 2015 by Istvan Sapudi and colleagues, using data from the Pan-STARRS survey and the WISE infrared satellite, identified a supervoid about 1.8 billion light-years across, making it one of the largest known structures in the observable universe, at approximately the right distance and in approximately the right direction to produce an integrated Sachs-Wolf cold imprint on the CMB. But here is the problem that has kept this story open rather than closed. The void, while real and genuinely large, does not appear to be quite large enough or deep enough to produce the full 70 microkelvin cold imprint on its own. The integrated Sachs-Wolf effect, from a void of the observed size and density contrast, should produce a temperature decrement of perhaps 20 to 30 microkelvin. The observed cold spot is roughly 70. The supervoid probably contributes something. It probably explains part of what we see. But the part it cannot explain has to come from somewhere, and that somewhere has been the subject of ongoing disagreement in the cosmological literature for years. Some researchers argue that the discrepancy reflects the difficulty of accurately characterizing the supervoid's properties from galaxy surveys, which are inevitably incomplete and subject to selection biases. The void might be deeper or larger than current surveys indicate, and better data will eventually show that it is sufficient to explain the cold spot after all. This is a reasonable position, and it is the one that most working cosmologists would probably cite as their default expectation. Others argue that the statistical significance of the cold spot has been somewhat overstated due to what is called a posteriori statistics, the fact that if you look at a complex dataset long enough and carefully enough, you will find unusual features, and the probability of finding something unusual somewhere is much higher than the probability of finding it in any specific place you designated in advance. The cold spot was not predicted before the CMB was mapped, it was found after the fact, and finding an anomaly after searching for it is statistically less impressive than predicting it beforehand. But then there are the more exotic proposals, and they deserve to be discussed not because they are likely to be correct, they are probably not, but because they illuminate something important about what the cold spot could mean if the mundane explanations fall short. The most discussed exotic explanation involves the multiverse. In the framework of eternal inflation, the inflationary process that drove the extraordinarily rapid expansion of the very early universe never fully stops. It continues forever in some regions of space, producing an endless series of bubble universes that nucleate within the inflationary background, each with its own laws of physics, its own constants, its own history. Our observable universe is one of these bubbles. In this picture, other bubbles exist, vast cosmic domains with different physical properties, and the inflationary background separating them is expanding so fast that they cannot communicate under normal circumstances. But under some conditions, two adjacent bubbles can collide, not gently, at velocities approaching the speed of light. And a collision between our bubble universe and a neighboring one would leave an imprint on the CMB, a circular region of altered temperature, colder or hotter, depending on the specifics of the collision geometry, with a characteristic profile that is in some respects similar to what we observe in Eridanus. This is, to be absolutely clear, highly speculative. The multiverse is not an established scientific framework. Bubble collisions are predicted by some versions of inflationary theory, but have not been confirmed observationally. The cold spot does not match the predicted profile of a bubble collision signature precisely enough to constitute evidence for one. Most cosmologists who work on this topic regard the bubble collision interpretation as interesting but unsupported, a hypothesis that cannot currently be distinguished from the supervoid explanation or from simple statistical noise. And yet the fact that such an explanation cannot be ruled out, that an actual feature in the most carefully characterized map of the early universe is ambiguous enough to be consistent with, among other things, a collision with a different universe says something about where cosmology stands right now. It is not a finished science. The most important observational dataset we have contains a feature that the standard model has not fully explained after decades of effort. In a universe that is truly isotropic, truly homogeneous, truly without preferred directions or special locations, the cold spot is exactly the kind of thing that should not require an exotic explanation. It should be a statistical fluctuation unlikely, but within the expected range of random variation in a Gaussian random field. The question is whether it is, and honest answer right now is we do not know. The supervoid helps. The statistics are debatable. The exotic explanations are speculative. The anomaly persists. It is a small flag planted in the data of the early universe, in the direction of Eridanus, noting that something here is unusual. Whether that flag marks a statistical accident, an unexpectedly large void, or something stranger, it has been there since the first full-sky CMB maps were made, and it has not been explained away. That matters for our central question, because the cold spot is a directional feature. It is in one place, not distributed randomly across the sky. In a universe with no preferred direction, no center, no asymmetry, a feature of this significance should appear anywhere with equal probability. It does not appear anywhere. It appears in Eridanus, and it sits in the sky as a quiet but persistent reminder that the perfectly symmetric, perfectly directionless universe the cosmological principle describes may have at least one exception, small, possibly explainable, but real, written into the oldest light we can observe. Which brings us to a second anomaly, less poetic than a cold scar in the ancient sky, but in some ways more statistically troubling, because it does not sit in one corner of the CMB. It shows up across the entire sky, in the distribution of the most distant objects we can detect, and it points in a direction that has no business pointing anywhere at all. Part 11. The Direction Problem. In 2018, a team of researchers led by Camila Bengali published an analysis of the largest radio galaxy surveys available and found something that should not be there. To understand why it should not be there, you need to understand what they were looking for and why the expectation was so clean and so well-founded that the discrepancy they found could not be easily dismissed as a measurement artifact or a poorly defined prediction. When astronomers survey the sky in radio wavelengths, they detect enormous numbers of distant galaxies and quasars, the brilliantly luminous cores of active galaxies powered by supermassive black holes, consuming matter at extraordinary rates. These radio sources are distributed across the full sky and in a universe that is truly isotropic, the same in every direction. You would expect to count roughly the same number of them in every patch of sky of equal area, after correcting for the known obscuration from the Milky Way's disk. Not perfectly equal, because random statistical variation means some patches will always have slightly more or fewer sources than others, but statistically equal with no systematic bias in any direction. Except there should be one small, predictable exception. We are moving. The local group is moving at 630 kilometers per second relative to the CMB rest frame in the direction of the constellation Leo. That motion has a consequence for how we observe distant radio sources. In the direction we are moving toward, the light from those sources is slightly blue-shifted, compressed to shorter wavelengths, slightly higher energy. This makes those sources appear slightly brighter than they would if we were at rest. And since astronomical surveys detect sources above a fixed brightness threshold, slightly brighter sources means slightly more detectable sources. In the direction we are moving away from, the opposite happens. Sources are slightly red-shifted, slightly dimmer, and slightly fewer of them make it above the detection threshold. The result is a dipole pattern in the radio source counts more sources in the direction of motion, fewer in the opposite direction, with a specific amplitude and direction that can be predicted precisely from the known velocity and direction of our CMB dipole motion. This is called the kinematic dipole, and detecting it in radio source surveys is not just expected, it is a fundamental consistency check on our understanding of cosmology. If the kinematic dipole in radio source counts matches the CMB dipole in direction and amplitude, everything is coherent. If it does not, something is wrong. Bengali's team found that it does not match. The dipole in radio source counts points in roughly the same direction as the CMB dipole, both toward Leo, which is reassuring, and suggests the signal is real rather than a systematic artifact pointing somewhere arbitrary. But the amplitude of the radio source dipole is 2 to 4 times larger than the kinematic effect alone can explain. The sources are more asymmetrically distributed across the sky than our motion accounts for. The excess asymmetry, the part that cannot be attributed to our known velocity relative to the CMB, has a statistical significance of approximately 4 sigma. 4 sigma means that if the universe is perfectly isotropic, as the cosmological principle requires, a discrepancy of this magnitude would appear by chance in fewer than one in approximately 15,000 random realizations of the sky. It is not impossible, but it is the kind of number that, in particle physics, would be considered strong evidence for a new effect. In cosmology, where datasets are messier and systematic effects more difficult to control, it is considered a serious tension. What makes this anomaly particularly stubborn is that it has not gone away as the data have improved. Bengali's 2018 paper was not the first to notice the issue. Earlier analyses using the NVSS catalogue, the NRAO VLA Sky Survey, had found similar hints going back to the 2000s and subsequent work using newer and larger radio surveys has generally confirmed the discrepancy rather than resolving it. A study published in 2022 by Secrest and colleagues, using a catalogue of about 1.3 million quasars from the Catwise survey combined with radio data, found a dipole amplitude inconsistent with the kinematic expectation at a significance of around 4.9 sigma, approaching the 5 sigma threshold that particle physicists use as the conventional standard for discovery. A different study using the RACS survey found similar results. The anomaly has been cross-checked across multiple independent datasets constructed using different instruments, different wavelengths, different source selection criteria, and different analysis methods. And it keeps showing up. The conventional scientific response to an anomaly like this is to look for systematic errors, and cosmologists have looked hard. Radio surveys are complicated instruments to calibrate. Different parts of the sky are observed to different depths depending on the survey design, creating non-uniform sensitivity that can produce spurious dipole signals if not carefully corrected. Nearby bright radio sources, powerful radio galaxies in our local universe, can contaminate counts if not properly masked. The calibration of radio flux densities across different frequency bands and different telescopes introduces uncertainties that are difficult to fully characterize. Any of these effects, if sufficiently large and directionally aligned, could in principle produce a false dipole signal of the observed amplitude. Many cosmologists believe that one or more of these systematics, once properly understood and corrected, will explain the discrepancy. This is a reasonable expectation. Systematic errors have explained away many apparently significant anomalies in the history of observational cosmology. But after years of scrutiny by multiple independent groups, the anomaly has proven resistant. Analyses that attempt to model and correct for the most plausible systematic effects still find a residual dipole larger than the kinematic prediction. Papers arguing that systematics are sufficient to explain the anomaly have been published and challenged. Papers arguing that the anomaly is real have been published and challenged in return. The debate is ongoing and has not converged on a consensus. The anomaly is not explained. It is, if anything, sitting more firmly in the data now than it was when first clearly identified. If the anomaly is real, if the excess dipole in radio source counts is not a systematic artifact, but a genuine feature of the universe, its implications are significant and uncomfortable for standard cosmology. A dipole in source counts larger than the kinematic prediction implies that the distribution of distant matter in the universe is not perfectly isotropic. There is more structure, more clustering, more asymmetry in the distribution of galaxies on very large scales than the cosmological principle allows. The universe, in this direction at least, at these distances, is not the same as it is in the opposite direction. That would be a violation of isotropy, not a catastrophic violation, not something that overturns the entire edifice of modern cosmology, but a measurable, statistically significant departure from one of its foundational assumptions. And now we arrive at the third anomaly, the one that has generated the most controversy, the most debate, and the most extraordinary proposed explanations of the three. It is called dark flow, and its story begins in 2008 with a paper by Alexander Koshlinsky and colleagues at NASA's Goddard Space Flight Center. Koshlinsky's team was using a technique called the kinematic Sunyaev-Zeldovich effect, which is a subtle but physically well understood phenomenon. When CMB photons pass through the hot gas that fills the space between galaxies in a galaxy cluster, the intracluster medium, they interact with the electrons in that gas through a process called inverse Compton scattering. The photons gain energy from the electrons, shifting to slightly higher frequencies. This produces a characteristic distortion in the CMB spectrum in the direction of galaxy clusters, a slight deficit of low-frequency photons, and a slight excess of high-frequency photons that is detectable with sensitive instruments. This is the thermal Sunyaev-Zeldovich effect, and it has been used extensively to detect and characterize galaxy clusters. But there is a second component to this effect. If the cluster itself is moving relative to the CMB, if it has a peculiar velocity, then the scattering also imprints a slight temperature shift on the CMB in the direction of the cluster, proportional to the cluster's velocity along the line of sight. This is the kinematic Sunyaev-Zeldovich effect. The signal from a single cluster is tiny, far below the noise level of any current instrument. But if you have hundreds or thousands of clusters, and if those clusters share a common bulk motion, if they are all moving in roughly the same direction because they are being collectively pulled or pushed by some large-scale structure, then stacking the kinematic Sunyaev-Zeldovich signals from all of those clusters can reveal a coherent pattern that rises above the noise. This is what Kashlinsky's team attempted. Using a catalogue of hundreds of galaxy clusters and the CMB maps from the WMAP satellite, they stacked the kinematic Sunyaev-Zeldovich signals and looked for a coherent bulk motion. What they found, they claimed, was a flow of galaxy clusters extending across a sphere roughly 1 gigaparsec in radius, approximately 3.26 billion light-years, moving at somewhere between 600 and 1,000 kilometers per second, in a direction roughly consistent with the CMB dipole. The scale of this claimed flow was the extraordinary part. Standard models of structure formation, seeded by the kind of random quantum fluctuations that inflation produces, predict bulk flows on the scale of 1 gigaparsec of only a few tens to perhaps 100 kilometers per second at most. Kashlinsky's claimed detection was an order of magnitude larger. It was, if real, completely outside the range of what the standard cosmological model could produce. The response from the broader community was skeptical but engaged. In 2013, the Planck satellite team, armed with CMB maps of far greater sensitivity and resolution than WMAP, conducted their own analysis of bulk flows using the kinematic Sunyaev-Zeldovich technique applied to a much larger cluster catalogue. They found no evidence for a bulk flow beyond what standard cosmology predicts. Their results were inconsistent with Kashlinsky's claimed detection. This appeared, to many observers, to settle the matter. Planck was the definitive CMB experiment of its era. If Planck did not see dark flow was probably not there. But Kashlinsky did not concede. Subsequent papers from his group, using updated cluster catalogues and refined analysis methods, continued to find evidence for the bulk flow. They identified what they believed were methodological differences between their approach and Planck's that could account for the discrepancy differences in how clusters were selected, how the CMB maps were filtered, how the stacking analysis was performed. The Planck team disputed these arguments. Other groups entered the debate, some finding hints of anomalous bulk flow, others finding nothing inconsistent with standard predictions. The literature on dark flow is a record of sustained, unresolved, scientific disagreement that has now lasted nearly 2 decades without producing a consensus. If dark flow is real, the implications go beyond anything else we have discussed. A coherent bulk motion of galaxy clusters across 3 billion light-years, 10 times larger than structure formation models can produce, pointed in a specific direction, would require a gravitational source of extraordinary mass, a source that cannot be accounted for by any known structure within the observable universe. The explanation that Kashlinsky and others have proposed is structures beyond the observable horizon. The observable universe is a sphere roughly 46 billion light-years in radius, defined by the distance that light has had time to travel since the Big Bang. Beyond that horizon, space continues possibly infinitely and contains matter distributed in ways we cannot directly observe. The gravitational influence of mass is not limited by the speed of light in the same way that light itself is. A sufficiently massive concentration of matter beyond our horizon could, in principle, exert a gravitational pull on the matter within our observable universe, producing a coherent directional flow that has no visible source and no explanation within the standard model. In other words, if dark flow is real, something beyond the edge of everything we can see is pulling on our corner of the cosmos, not a center of the universe in the classical sense. There is still no privileged point, no origin, no cosmic ground zero, but there is a direction imposed from outside, a gravitational whisper from beyond the horizon, telling every galaxy cluster within 3 billion light-years which way is down. The universe may not be perfectly homogeneous beyond our horizon. Inflation, in its standard formulation, predicts that the universe beyond our horizon should be statistically similar to the universe within it, the same average density, the same average structure, the same laws of physics operating in the same way. But inflation also allows for scenarios in which the initial conditions were not perfectly uniform on scales larger than the observable universe, in which case our horizon might be sitting inside a region that is itself embedded in a larger asymmetry we cannot directly map. What if we are not at the center of the universe, but we are also not in a perfectly centerless universe either? What if the answer is not the clean philosophical resolution that modern cosmology offers no center, no preferred location, pure democracy of position, but something stranger, something that lies in the gap between the ancient intuition and the modern dismissal? What if the universe is centerless in the global sense, but asymmetric in the local sense? Not because of anything special about our position, but because the region of the universe we can observe happens to be embedded in a density gradient that extends beyond our horizon, pointing in a direction we can measure but never fully explain from the inside. These questions are not answered. They are, in the most honest scientific sense, open. The three anomalies we have examined, the cold spot, the radio source dipole, the dark flow, are each individually ambiguous. Each has possible mundane explanations. None of them, alone, is sufficient to overturn the standard model of cosmology, but they point in the same conceptual direction. They all suggest, with varying degrees of persistence, that the universe may be less isotropic, less homogeneous, less perfectly symmetric than the cosmological principle requires. And if even one of them turns out to be real, unambiguous, and inexplicable within the standard framework, the question of what exists at the center of the universe will stop being a question about whether the center exists and become a question about what is generating the direction we keep finding ourselves aimed at. Part 12. The question that refuses to die. Let us come back to where we started. You are sitting on a planet, orbiting a star, in a galaxy that is moving at 630 kilometers per second toward a gravitational anomaly 520 million light-years away, inside a supercluster whose boundaries are defined by motion rather than position, in an expanding universe that has no center because its origin was not a place but a condition, whose spatial geometry on large scales is flat and smooth and homogeneous, but which on smaller scales organizes itself into filaments and nodes that each behave like local centers, and which shows, at the very edges of the data, at least three anomalies that standard cosmology cannot cleanly explain. The global picture is clear. The universe has no center. The cosmological principle, while not perfectly confirmed, it never can be, since we can only observe within our horizon, is supported by an overwhelming body of evidence. The CMB is isotropic to 1 part in 100,000. Galaxy surveys across billions of light-years show statistical uniformity above the scale of a few hundred megaparsecs. The Big Bang was not an explosion at a point. Expansion proceeds equally in every direction from every observer's frame. The geometry of space-time on cosmic scales does not privilege any location over any other. If you could teleport to any random point in the observable universe and look at the large-scale distribution of galaxies around you, it would look statistically similar to what we see from here. That is what it means for the universe to have no center. But the local picture is equally clear, and it tells a different story. The local group is moving at 630 kilometers per second. That motion is real, measured, gravitationally induced, and shared across thousands of galaxies in our region of the cosmos. The Great Attractor is real. The Shapley supercluster is real. Laniakea is real. The dipole repeller is real. These are not artifacts of imprecise measurement or mathematical formalism. They are the actual gravitational topology of the universe in our corner of existence, and that topology creates directional flow, local hierarchy, and structures that function as centers at every scale they operate on. The reconciliation is this: global and local are both true, and they are true at different scales. The universe has no center globally, it has many centers locally. The cosmological principle applies above the scale of a few hundred megaparsecs, where structure averages out. Below that scale, the universe is anything but uniform, and the complexity of that non-uniformity is what produces the peculiar velocities, the gravitational basins, the attractors and repellers, the flow fields that we have been tracing throughout this conversation. What the cracks in the data represent: the Hubble tension, the radio source dipole, the cold spot, the disputed dark flow, is the question of whether that reconciliation is complete. Whether the scales at which the cosmological principle holds are truly as large as we think. Whether the structure beyond our horizon is truly as random as inflation models suggest. Whether there is something out there in the darkness, beyond the last photon we can detect, that breaks the symmetry in a fundamental way. These questions are not answered. They may not be answerable in the current era of cosmology, given the fundamental limits set by the observable horizon. There is only so much universe we can see, and the anomalies we have been discussing are precisely the kind of signal you would expect to find if the universe beyond our horizon were not a statistically perfect reflection of the universe within it. Now think about the layers of motion you are carrying right now, sitting in whatever chair or room or field you occupy at this moment. Earth rotates at roughly 465 meters per second at the equator. Earth orbits the Sun at about 30 kilometers per second. The Sun moves around the galactic center at about 220 kilometers per second. The Milky Way moves within the local group at several tens of kilometers per second. The local group moves relative to the CMB at 630 kilometers per second. All of these motions are real. All of them are happening simultaneously. You are not stationary in any meaningful physical sense. You are a passenger on a nested series of orbits and infall trajectories that compose, at the largest scale, into a directed plunge toward the Great Attractor and the Shapley supercluster beyond it. And here is the thing about that plunge: it will never reach its destination, not because the destination does not exist, it does, and it is genuinely enormous, but because the universe is expanding, and as the distances involved grow large enough, the expansion of space will outrun the gravitational infall. The peculiar velocity that carries us toward Shapley will eventually be overcome by the recessional velocity generated by expansion. In the far future, if you could somehow wait long enough, the Great Attractor would still exist, its mass unchanged, its gravitational field still curving space-time, but every galaxy currently falling toward it would eventually stop approaching, because the expansion of space between us and it will have grown too fast to overcome. We are falling towards something we will never reach. There is something almost mythologically appropriate about that. The universe constructed its most compelling gravitational centers, then arranged its expansion to ensure that no one ever arrives. The architecture of the cosmos is one in which direction exists without destination. Motion exists without terminus. Structure exists without center. The concept of center itself turns out to be a human import. We brought it to the universe from our experience of objects with edges, rooms with corners, maps with legends. The universe borrowed the concept for a while, tolerating Aristotle's Earth and Ptolemy's celestial spheres and our intuitive reaching for a fixed point, and then proceeded to demonstrate, in stages spread across millennia of observation, that no such fixed point exists. Every center we have ever identified has dissolved, under scrutiny, into a local feature of a larger pattern. Every pattern we have identified has dissolved into statistical smoothness at sufficient scale. The center retreated from Earth to Sun to galaxy center to nowhere in particular, and at each step the universe was not hiding the center. It was showing us that the center was a question we were asking about the wrong kind of thing. And yet, the motion is real. The anomalies are real. The direction is real. The universe does not have a center, but it is not directionless. And something, somewhere, perhaps within the observable universe, perhaps beyond it, perhaps in a structure so large our descendants will spend centuries mapping, it is still pulling. Not because it is the center, but because that is what mass does. It pulls, it organizes, it creates local topology in a globally centerless space. The way every river carves a valley without the planet having a true center of drainage. Every valley is a center for its watershed. No valley is the center of the world. And the universe, if it is like anything, is like a world with no special valley, no privileged watershed, no apex toward which all rivers run. Only rivers. Rivers everywhere, each of them falling, none of them arriving, all of them moving in directions that feel, from inside, like purpose. You are on one of those rivers right now. You have always been on it. You will always be on it. And the universe, for all its staggering emptiness, its incomprehensible scale, its refusal to place anything at its heart, has arranged things so that wherever you happen to be, you are surrounded by structure, embedded in flow, aimed at something and close enough to the center of your own observable cosmos that every direction you look carries exactly the same distance to the horizon. The universe does not have a center, but it is not directionless. And something, somewhere, is still pulling.